is a star. Notice this star is all by itself. There are no other stars nearby. So this star, which we could call something like our sun, is what's called a single star system. Okay. Single star systems just mean there's one star and that's it. It could have stuff orbiting it, it doesn't have to, but there's only one star. Now some stars out in space are part of what's called a binary star system. So I'll write that up here. A binary star system means there are two stars. So let's add another one. Now binary star systems are kind of cool. Sometimes the binary star systems orbit in a circle around some fixed point. Sometimes, when one is really massive, the smaller one will actually orbit around the big one while the big one barely moves. Some binary star systems have a case where when this star gets close, the big star actually pulls gas in off of it, and this, whoops, I just moved my whole stack of paper. Try again. When this little guy gets close to it, it sucks in some of its gas, and this guy flares up really bright, which is called a nova. And a nova is typically a type of a binary star system, or it's a product of a binary star system, I should say. So anyway, binary star systems have two stars. Now, in space, they're not all single star systems. They're not all binary star systems. Some of them are what are called multiple star systems, which means instead of two, you might have three orbiting each other. Sometimes 4, 5, 6, and the most I think we've ever seen is 7. Now, just for kicks, I want you to imagine this is our star, and here we are, we're the Earth, orbiting this star. As these stars all orbit each other, could you imagine having multiple stars up in the sky at the same time? Anyway, deep thoughts on a Tuesday, I guess. Our next topic is stellar magnitude, which is just a fancy word for a star's brightness. Now, in the picture, you can see, here we've got the Earth, here's you. You're looking at some stars. Now, obviously, some of the stars are brighter and some are dimmer. And if you've ever been outside at night, you'll know this is the case. And we generally look at those big, bright ones. We have a rating scale for those. It's called the magnitude scale. And in this case, what we're going to talk about is apparent magnitude. Apparent magnitude is how bright a star appears when you're standing on Earth. So, in this scale, this guy right here, we'll say he has an apparent magnitude of negative 0.2. I'm going to say he has a magnitude of positive 0.3. He has a magnitude of positive 2.1, and he has a magnitude of, we'll just say positive 3.0. Now, what do you notice? This seems kind of weird. Usually, bigger things get bigger numbers. In this case, this rating scale is kind of backwards. Brighter stars have lower magnitudes. Dim stars have higher magnitudes. Just to give you a good example, the sun, I'm not sure why the sun is green, but it is. The sun has an apparent magnitude of negative 26.7, which is as bright as it gets, at least for Earth. So anyway, that is the rating scale for apparent magnitude. All right, next we want to talk about distances to stars. One of the hardest things about studying stars is that we are stuck down here on Earth. Other stars are quite a ways away from us, and the term that we use to measure distance is called a light year. Shockingly, a light year is simply the distance light can travel in 1 year. And if you think about it, light is simply energy. And so let's take this little orange star up here. It has nuclear fusion going on, which gives off energy. That energy has to travel in wavelengths all the way down here to Earth, right? Now, obviously, that can't happen instantaneously. That has to take time for the light to travel through space. So let's imagine this star, the energy took 1 year to reach Earth. That star would be at a distance of 1 light year. Now, the cool part here is that if this is you, and you're looking at that star, when this light hits your eye, what you're actually seeing is light from 1 year ago, because the light has physically been traveling, that image has been traveling through space for a year. So when you see this star, let's say you went outside and saw this star tonight, you're actually looking at what this star looked like 1 year ago. If you want to see what it looks like right now, you'd have to wait another year and look at it again. And again, it'd be 1 year old. So really what you're kind of doing, hopefully you're watching this on Thursday, so this can be Deep Thought Thursday. Every time you're looking at a star in space, you're actually looking back in time because you're seeing what that star used to look like. So let's go a step further. This big orange star over here is even further, and the light is traveling at the exact same speed to reach the Earth. This guy we'll say is, I don't know, 4.6 light years away. That is actually the distance to the nearest star to Earth. So if you went outside at night and you wanted to look at Proxima Centauri, it's 4.6 light years away. That means this light has been traveling for 4.6 years. So that means the closest star to us, when you look at it, you're actually looking 4.6 years back in time. And obviously when you have stars that are even further, you're looking back in time even further. The fun part is when you start looking at galaxies, galaxies are hundreds of thousands of light years away. Sometimes even further than that. So when you start looking at things deep in space, what you're really doing is looking way back in time. So as we build more powerful telescopes, what that allows us to do is look further and further back into time. Okay, last deep thought. It's simply this. Anytime you're looking at anybody else, to see them, the light has to be bouncing off their face, we'll say, and hitting the back of your eyeballs for your brain to process it. So every time you're looking at somebody, you're actually looking at what they used to look like a fraction of a second ago. Okay, time to talk about the size of stars. For starters, there are 5 general categories that we use to describe the size of stars. The first one is the smallest, and that is what's called a neutron star. A neutron star is very small. They're incredibly dense, like ridiculously so, but a neutron star is about the size of, I usually use this example, from Napoleon to Vandercook. Take that size, wrap that into a sphere, and that's the size of a typical neutron star. They can be a little bit bigger, a little bit smaller, but that's about how big they are. So in terms of things in space, that is really, really tiny. Next size up is what we call a dwarf star. Now, a dwarf star is about the size of, say, Uranus or Neptune, one of the smaller gas giants, one of the smaller Jovian planets. So as far as stars go, they're not very big, but they're there. They're visible. They have gravity. The next one's a little more familiar, and that would be this guy. This is called a medium-sized star. This is the size of our sun. This is actually the size of most stars, and they're average medium-sized stars. Now, as we move on, we've got a bigger category. The next category up, let's make it blue, is a giant star. Now, a giant star, to imagine the size, you would have to take our sun out of our solar system and put a giant star in its place. If you did that, it would occupy all of the space of the asteroid belt and the inner planets. So Earth would basically be inside that star. So that's a pretty big star. That's pretty big. Not near as big as the last category, though, which is a supergiant star. Now, supergiant stars are, as they say, supergiant. If you were to remove the sun and put a supergiant in its place, it would actually occupy all the way out to probably about Neptune, which is most of our solar system. So in other words, the size of supergiant star is almost as big as our solar system. All right, ladies and gentlemen, last lesson for this week, and that is stellar temperature. To tell how hot a star is, it's as simple as looking at its color. So, as you look at this list right here, you'll notice I start out with red. This is the coolest temperature of star, which is ironic because obviously we think of red as a hot color. In stars, red is the coolest type of star. And as you work your way up this way, they're going to get warmer and warmer. So it goes from red to orange to yellow. I didn't know how to draw white on white, so I just wrote the word white. And then the hottest color is going to be blue. So as you go outside and do your observation this week, I hope you think about when you're seeing stars that are blue versus stars that are white versus stars that are orange versus stars that might be a yellow color. Really what that's telling us is how hot that star is. And as we're going to find out next week, the size of a star and the temperature of a star have a lot to do with its age and what it's going through inside right then. So there you go. Red's coolest, all the way up to blue being the hottest.